XDF doing FPGA programming in Sans Holiday Hack Challenge. We have this goal of we have to program the FPGA for this doll to make a square wave at a given frequency. There's going to be a handful of inputs. So we have a clock. So it's probably pretty hard to read, but the clock is going to be 125 megahertz, so that's very fast. And then we're going to have a reset button. When that goes high, then everything should reset. And we're going to have a 32-bit frequency coming in, and that's going to be represented as some value from basically 0 to 10,000 with 2 decimal places per hertz. And I need to produce a square wave out that looks like that frequency. So, they put some junk here that doesn't matter, but we'll need to build off of that. Now, if for background, I was brand new to FPGA programming. You can't think about this like regular programming. In fact, it's worth. There's a YouTube presentation from Professor Cordy Bite that talks all about how to do this, and I took a lot of notes from that, and that's really what I'm going to base my solution off of. So the first thing I wanted to do was I didn't want to try to worry about making it variable frequency. Just can I produce a 500 hertz wave? And so to do that, I am going to start off with, so you've got these inputs, and it says don't mess with that, and it says basically you want to start here. So we're going to get rid of this. And so now what we're going to do is going to do always, and again, this is just straight out of the presentation, pause edge on the clock, or pause edge on the reset. If either of those have happened, then we're going to do a begin if reset equals 1, begin, no E there, counter, we're going to set to 0. We don't have a counter, we need to make one. Do that up here, so we'll come here and we'll do reg, we're going to have a 32-bit counter. All right. And we're going to just and again, like he does in the presentation, we're going to make a register called wave, and we're going to assign wave out equal wave. So now we can set the register there, and it will affect the output. It's not clear to me why I can't just set wave out, but it didn't. I don't think that seems to work, so we're going to go with this. So when we begin, we're going to set counter to 0, and we're going to set our wave to 0. Pretty simple. We will end this, and now, oops, we'll else. So else means we are now here working off of the raise of one of our clock edges, and our clock is going to, 125 megahertz is very fast, so it's going to happen a lot. So basically, we want to do, we're trying to do 125 megahertz, and that is going to be twice that number of edges because the edges happen on the up and the down. So we have, let's see if I can pull a calculator up here, or that. Let's go to decimal here. If I have 125 megahertz, so 125, that's 25 hertz, kilohertz, megahertz. So if I do 1 over that, that means I'm going to get an edge, a positive edge, the beginning of a cycle every that many seconds. So very few. If I want 500 hertz, so that's 1 over 500. I need to figure out how many steps are in. Is this making any sense? I need to figure out how many steps I have to do to get, how many of these little blocks I do to get to 500. So if I do 1 over 500, that is 0.02. So I want to know what that is divided by 1 over 125. So really just times 125, 123, 123. And that tells me right there I need 250,000 cycles in my clock of my 125 megahertz clock to get 500 hertz to trigger at 0.002, which is 500 hertz. Now, I believe this pause edge clock happens on either edge, so I actually only need half as many of these. But let's try it. We can start off with this. So let's start here. We'll come down here and we'll now say else begin if counter greater than or equal to this. Begin counter becomes 1, and it becomes 1, not 0, because we're counting the clock edge. This still counts the clock edge, even though it's reset. And wave, we're going to set it back to wave XORed with a 1-bit binary 1. And this would be else. So if the counter's not ready to loop around, we're just going to do counter becomes counter plus 1. And so we can now, that else is done. Oops, what did I do? Come down here, end this line. We're done with the else. We can end this. We can end this, and we still have an end module there. And so we can try to run this. And so what we can do to run this is hit simulate 500, and we get an error. And let's see what our error is here. Tone generator syntax error on 37. Probably because I'm missing semicolons. Python programmer here, clearly. I'm missing any other ones. There's counter. Let's see, let's try it again. It's loading up. So it's going to complain here that the signal frequency is not used. It's just kind of a pain because I don't want to use the frequency yet, but I can't delete it from here. It'll yell at me too. And so the solution I came up with for this was to do or freq equals 1, 2, 3, 4, 5. So as long, I mean, this, if I actually got the input frequency of 1, 2, 3, 4, 5, this would really 6. This would break horribly, but since I know I'm setting 500 hertz, that should be good. So what happens if we do this? Oh, I don't want to do equals. I guess I need to do double equals. Is that what I needed? It's running the simulation. And I'm getting a frequency of 250 hertz, and I needed to get 500. And so that's where I was talking about before about how I was unclear about my counters. So really, I just need to, if I'm only getting 250, I need to happen twice as fast. So I need the counter to basically come early. So I'll just cut that number in half, and I will simulate 500 hertz. And let's see if we can get it. It's taking a few seconds. Congratulations, we got 500 hertz. So by this logic, if we wanted to get 1000 hertz, we would divide this in half again. So this 12 would become a 6, and the 5 would become a 25, and we'd end up with that. And let's come up here and see if we now try to do 1000. We're getting exactly 1000. This is working really well. So now the challenge is I don't want to have to do this manually. I want to set this thing here to be my based on the frequency input. And it took some thinking here to get this right. Let me see if I can find I can actually pull up a calc and leave. We'll do this kind of manually here. So I know if I'm doing 500, if I want 500 hertz, I know I need it was 12, it was twice this, right? Let's grab this. Put this here, and then we'll make this 12. Was it exactly that? Let's see. This times 2 becomes that. There we go. That was easy. For 1000, we know we want that. So I'm gonna guess for 2000 megahertz or hertz, I believe it was. We're gonna want 3, 1, 2, 5, 0, like that. So the question is, can we calculate that? We know our clock is 125, 1, 2, 3, 1, 2, 3. And so can we do something here? So say this is equal to, and we did it before, it was actually that divided by this. Is that correct? Yep, divided by 2. like that, and that works. So let's see, which one do we want to stay the same? We want B to stay the same here, so we'll do this, and then we can fill these down. I probably should be zoomed out. It's hard to read. And that works out perfectly. So we have a formula here where we're going to take the clock frequency, which we know, and we're going to divide it by, we're going to take, basically what we can do is we're going to divide it by 2. So we can do equals that divided by 2, just get that number, and then we can take this, we'll just move this over here. We'll get rid of the divided by 2. We now have a formula that works. So the answer is this constant number, 625, blah, 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 divided by the input frequency. So how are we gonna implement that in our FPGA language here? So what we basically need to say is if counter is bigger than, and that's where we're going to say where was our number here. Grab that sheet. This, we need to get this number. We might need to copy, paste this. Let's see, paste special number. Grab that. Okay, I want that number. So I want this number, and then I want to divide that by freq, and get that, and basically get this output, get this counter. The problem is I'm dealing all in whole numbers, and dividing like this is going to be really painful. And it took me a while longer than I'm proud to admit to think of this. But really what I can just do is do freq times the counter. And if that's greater than or equal to this number, then I am done. So let's try that up here with the simulate 1500. And I think it's probably going to fail still, but let's see. For some reason here, and I can't quite, I can't explain it. So I'm off by a factor of, I'm trying to get 500 and I got 50,000. And the reason is because the frequency coming in is, it's an integer, but it's got, I'm supposed to treat it as the low 2 bytes are decimal places. So I actually need to I need this to get bigger. I need to multiply this by that much bigger, because this frequency thing, I really need to multiply both sides. I need to multiply this by, well, I'm dividing this by 100. And so to get rid of it, I need to multiply this side by 100 and clear that out. And so we're feeling pretty good about ourselves. We can run this here, and we get this problem where it's telling us that 625, all these zeros, can't fit in a 32-bit number. And so the way you do this, and this is what took me probably the most research of all this problem, was just trying to figure this out, is I can say 64D, and what that does is it says make a 64-byte decimal value this. So now when I run it, it works perfectly. I can do a simulation of 1K without changing my code at all, and it works perfectly. I can do the 2K, and it works. We can do a random frequency, see what we get. So, you know, it's the target frequency was this. The closest I was going to get was that, and I got that, so that we did good. So then we can simulate frequency. Oh, that'd be, we got to do a random frequency. Sorry. I don't know why my play sound button went away. Okay, so we're still close, but not quite right. Oh, it's letting me have the play sound, and oh, I don't know if you can hear that, but that sounds terrible. Thank you, Karen. So I think that's success in this challenge. We'll do program device. That'll work. Sending source code for analysis, and I've unlocked the challenge. I've succeeded. And you think you're done here, but this took me longer than I'm happy to say. If you click over here, so actually when I get that, I get an item here, and I now have a second item, my programmed FPGA. If I click over here, I can take that FPGA and put it in here. And now I unlock the final narrative. The spaceship comes down, and I get to learn that Jack Frost is from outer space, and you know, Santa has been actually talking to his home planet and is going to get him to come take him home. So we can go. Whoa! Let's go into the spaceship. We can see the final credits here. Here's Santa. I need to zoom out a little. Reset my zoom here. Anyway, here's the final credits, and we talk to these people. They tell us all about how they're coming in peace. They're going to take Jack Frost home, and fill in the rest of the narrative. And that's the end of the Sans Holiday Hack 2021. Jack Frost is not too happy to be sent home, and Santa's pretty happy that we saved the day. So we achieved the victory here. Thank you so much to Sans, It's Gotis Counterhack team. This was a lot of fun as always, and I look forward to doing more of these in the future. Thank you for sticking around to the end.